Section 13.3, gravitation near Earth's surface. So if we take Newton's law of gravitation, F equals big G, the universal gravitation constant, times the mass of the Earth, the mass of an object like our apple, divided by r squared, and set that equal to ma, F equals ma, where the acceleration we say is acceleration due to gravity. What we notice is that the mass of, say, our apple is going to cancel out of both sides, and we get that the acceleration due to gravity is big G, big M, divided by r squared. And this gives the magnitude of the gravitational acceleration at a given distance from the center of the Earth. So the r here isn't to the Earth's surface, it's the full radius of the Earth and any distance beyond. So if you calculate it right at Earth's surface, at the full radius of the Earth, and you plug that in along with the mass of the Earth, that's what the big M is here, it's the large mass that's pulling the apple towards it, you'll find that the acceleration due to gravity is about 9.83. So that's the average value on the Earth's surface. We find, for us, it's about 9.8, but this is just the average value due just to the gravitational force. Notice though, as we move further and further from the center of the Earth to larger and larger altitudes, the acceleration goes down, right? As we're pulling further apart at a greater distance from the Earth, then that's going to be less and less force, and so there's also less acceleration. So a communication satellite has barely any gravity that's holding it in place, keeping it in orbit as it orbits around the Earth, which is pretty cool. Now, this calculated value will differ slightly from the measured G at any location, right? We saw how we could measure G using a pendulum in lab, where we set the pendulum up, time its period, get a really accurate period, really accurate length, and we're able to calculate a measured G. But it's slightly different than this calculated A sub G. So the calculated one won't match the weight for about 3 reasons. One, Earth's mass isn't uniformly distributed, which is shown in this figure, right? Earth has most of its mass at the inner core, or the highest density of mass, I should say, excuse me. And that density decreases rapidly, so that the surface, it's so much less dense than anything else, it doesn't even appear on the graph, right? This is the surface here, and it's somewhere down in the 0. Also though, Earth is not a sphere, right? A sphere would be if it was perfectly round in all directions. It's actually technically a little wider in the middle, and it's what's known as a geoid, where there's mountains and valleys, and so it's not a simple spherical mass distribution. And then the other factor is that Earth rotates, and due to this rotation, the measured G is going to be slightly different than this calculated value. The calculated value is still really useful for giving you a mean value that you could use even for calculating the acceleration due to gravity on other planets, like on the moon, which is pretty nifty, or planet X, if you just knew the mass and the radius of planet X. All right, but this rotation, we can see how that will affect our measured G value. So if we imagine putting a crate on a scale that's right on the equator, then as the Earth rotates around, the normal force is pushing up, the gravitational force is pulling the crate down towards the center, right? So we have the normal force up minus the force of gravity pulling it down. And here we're using A sub G because we're using the calculated value. F net is equal to mass times acceleration. Well, notice the crate is rotating, it's moving in a circle. That means it will have acceleration, a non-zero acceleration. So our centripetal acceleration can be calculated with v squared over r, or omega squared times r, where omega is our angular velocity. And that is negative because it's in the negative radial direction. It's going inward, it's going in the same direction as the force of gravity. So if our normal force, if we assume that that's mg for a moment, then that can give us an apparent weight right? The normal force is really our apparent weight, what the scale reads. And so we can use mg for that. And the measured g that our scale would tell us is equal to the calculated a sub g minus this rotation, right? And so that can help factor in why it's 9.80. That's the value that we use for g, as opposed to 9.83 or something like we saw in the last one. So we don't need to account for this too often. The more important equation is that we can calculate the acceleration due to gravity with that first equation, g big M divided by r squared. So that's the important takeaway from this section. But then just noting, g does have some different values depending on where you are on Earth, which is why there are scientists who actually spend a lot of time and energy trying to measure that accurately. So that's gravitation near Earth's surface. We could also imagine gravitation inside Earth. And this is going a little deeper. It's not something that's totally critical, but it's useful to see. So the shell theorem says, we already saw that if you're outside some mass that's a shell, then you can treat it as though all of the mass is at the very center of that shell. On the flip side, a uniform shell of matter exerts no net gravitational force on a particle located inside of it. So once you pass inside the shell, it's not that all of the forces disappear, but their vector sum comes to 0. So they all balance out no matter where you are inside that shell. So that's the most important part of this section. For a little bit of fun, we could find the gravitational force inside an assumed uniform density Earth. So this is a simplified scenario. We're going to assume it's a solid sphere, right? Well, we know it's a solid sphere. It's not a shell. There's definitely mass in the middle of it. And so we can say the force is going to be g times the mass of our object that is passing through the center of the Earth times the mass that is inside, right? So that's shown by this dotted line, because everything outside is not going to contribute any gravitational force. Now, because we're assuming constant density, then the density will be the same for the amount inside our particular location, so the mass inside divided by the total volume for pi little r cubed, where r is that distance to where we are located. And that will be equal to the total density, which has the total mass divided by the total volume. Big R here is talking about the entire radius of the Earth. So if you substitute this relationship into the first one, we get that the force is equal to g times the mass of our object times the mass of the Earth divided by the radius of the Earth cubed times r, our position relative to the center of the Earth. So if we write this as a vector equation and say that everything in front of the r is just k, some constant, then we find that the force is equal to negative this constant times the radius vector. It's always pulling inward to the middle, which is what the negative says. And this looks exactly like Hooke's law. The force is negative kx, or kr in this case. In other words, if you had a hole drilled through the center of the Earth all the way through to the other side, and you dropped an object there, it would oscillate. It would feel the largest force when it's at the largest radius, and then it would speed up and feel no force at the very center of the Earth, but it would have a lot of velocity. So it would keep moving down through the Earth, and it would feel a force slowing it down until it reaches the other side of the Earth, where it would briefly stop and turn and start to accelerate the other way. So we'd see the object bouncing up and down. In the absence of air resistance, it could do that forever, which is pretty wild. So that's a fun little aside. The important part with this shell is really the shell theorem, that once you're inside a shell, then there's no net mass acting on you. All right, we will wrap that up there.